Alrighty, so I'm making a video here of memory, trying to remember what we did this morning and give you another opportunity to try those problems again, obviously at your own pace. So you just hit that space bar, pause the video, and take as long as you want with each problem. But I'm just going to do them in a moment, so I'm not here all day long. I'm just going to fly around the room. What else did I want to say? So there's going to be a mixture of some basic skills, a lot of them, things that you practice in Algebra 1 and Algebra 2, a mixture of some new conceptualization, some new problems in terms of what you've covered in this class, mostly unit circle work and how to write an exponential function we did at the end of the class, and certainly not enough practice for you to have a handle on it yet. But this class, I think you probably, towards the end of the week here, certainly not my D block class, isn't having this experience yet because I've only seen them once, but A and B, it's 3 days in a row. Okay, so tomorrow, whatever we did on day one, I'm hoping for a lot of you feels a whole lot different. All right, and so therefore, this is kind of like a dog. I can't draw. There we go. How's this for a dog? Does this look good? A little neck and little mouth and little eye. There's my dog. Looks more like a turtle. All right, well, I need a tail, so it's going to dog now. All right, so day one, hey, not much understanding, maybe hidden in the old brain, but by day 4, yeah, enough practice. Hopefully it starts to end up where it's supposed to be. All right, so I'm glad I'm doing this video right now, because from 2 hours from now, I'll probably fall asleep. Grandpa needs this nap. All right, so I'm going to end with showing you where we're eventually going with the trigonometry and how it ties into some things you've already studied. So I am going to give a lecture on one problem at the end. Everything else is pretty basic. Did A block cover every problem I'm going to do? Maybe not. Did B block cover it? No, I mean, we get into different things as we start talking. So well, I guess it's me talking most of the time. All right, so I'm just going to start. I'm going to fly through it. I am going to layer some stuff towards the end of this video. Let's have at it. All right, sine is 17 pi over 6. You want to do them in your head, so I think the answer is a half, but let's see. So we got a circle. We got 6 parts. All right, so which means there's 12 altogether. 12 parts in the circle, right? Boom, 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 boom. There's 12. I got to get to, and we start here at 0, 1, 2. We count that way. I've got to get to 17, which is right there. So I pictured it correctly. That is an altitude of a half because the reference angle is 30 degrees. So I really went 360 and 150. So I really went 360 and another 100, 460 and 50, 400, 510 degrees. So this is also 510 degrees, but this is all about the distance, radius lengths. So if I have a radius, do I have my lanyard? Come on, lanyard. So this does have a radius. Pi is 3.14. 3.14 divided by 6 is close to a half. Half of 17, 8.5. So if I have a radius here, I should do 1, 2, 3, 4, 5, 6, 7, 8.5. Radius length takes me there. And sometimes I think I shouldn't write pi. I should just write 3.14 and say what I just said a minute ago. That number of radius lengths, where does it take you on the circle? And then you make your triangle. All right, so 29 pi over 6 is, well, we already got the chunks of 6. We might as well use this circle again, save some time. So I see 24 pi over 6. Nice even number, 4 pi. That's twice around the circle. 2 pi is once, 4 pi is twice. And I got to go, it's the same triangle. How did we luck out here? It's coterminal. Oh my God, how didn't I know that? Should be, yeah. I mean, if you add 12 to 17, you went around the circle one more time. My God. So the cosine is minus root 3 over 2. It's the width. All right, because hypotenuse is 1. Doesn't matter where we are. The hypotenuse does not change signs. So negative root 3 over 2. All right, so now we're going to go over and we're going to put this in graphing form. Show you a little shorter way to do this later, but right now, hopefully it makes sense. We talked about getting the first term. We got the first term. We need the second term. So to get the second term, I'm going to make that positive 12, and I'm going to divide by 2 times 3, which is 6, which gives me an x value of 2. And I want to minimize, because I know this is a cup shape up, I want my minimum to occur, and that occurs when I do 0 squared. I'm working with the number 2, so that's why I say x minus 2. That creates a minimum at 2. Okay, I put 2 in, and I'm going to get that signature 2 to 1 ratio. There's geometric reasons for that. Later in the year, I'll show it to you. So that's minus 12 plus 8. Minus 12 plus 8 is minus 4. And if I really want to graph this, I should take the y-intercept, which is 0, 8, and just throw it in there as well. All right, so this thing does have some real roots. We talked about that, so I forgot to put this here. So we also practiced doing this out, so let's do it out real quick. We have practiced squaring a binomial. So x squared minus 4x plus 4. And then subtract 4, and that gives me 3x squared. Yay! Minus 12x, yay! 12 minus 4, yay! Okay, so same exact calculation. Yeah, I am slowing down here, aren't I? All right, so what do I have to do to get to a height of 0? From a conceptual standpoint, minus 4 has got to go up 4. I've got a multiplication by 3. That's going to go there. I got the plus minus square root, and I'm centering this thing at 2. Those are the roots. This number is just a little bit bigger than 1, and 2 minus 1. So maybe we're at 0.7 or something. I don't know. I know that this is 4/8, right, because of the symmetry. So I know I'm somewhere between 2 and 4. So if I add a 0.7 to 2, well, I said it's bigger than 1. If I add 1.1 to 2, 3.1, yeah, that's between 2 and 4. So it's nice to get a little feel for that. Moving right along, or should I say now for something completely different. Give Monty Python a little shout out. Yeah, I think you can see that. No, I don't think I can survive long in the ring. All right, 27 to the negative 2/3. We talked today about what those 3 operations are. Any order is fine. Right now it's 27 over 1. That minus sign is going to flip the fraction. I know how to square. The question is, do you remember what the 3 means? Cube root. So the cube root of 27 is 3. That only leaves me 3 to the negative 2, which is 1/9. Okay, so that's using an exponent. These problems ask you to find the exponent. This right here is all about 8 to the what equals 1/4. That's what this command is all about. It's trying to find the exponent on top of an 8 that gets you a 1/4. Maybe knowing that we have 3 operations, powers, roots, reciprocation, maybe you can just look at the number 8 and say, what do I have to do to it to get it to be a 1/4? Well, what number do they seem to have that's in common? Hope you said a 2, because 8 could have been written as 2 cubed. And I could have put the exponent on top of 8 that way. And I think I can express 1/4 as a base 2. We just did it back here, right? 3 to the negative 2 is 1/9. So 2 to the negative 2. And so therefore, power to power is multiplication. So if 2 to the 3x equals 2 to the negative 2, I got a feeling 3x equals negative 2. So negative 2/3. So let's look at 8 to the negative 2/3. Oh, cube root of 8 is 2. 2 squared is 4 with a minus sign. There's a reciprocation, getting us 1/4. Okay, so we'll be practicing that. That's supposed to be review. Now, feel free to keep doing this. But eventually I hope you can see that you're multiplying 7 times 2i and you're multiplying 7 by 2i. That happens twice. And I think you're squaring the 7s, and I think you're squaring 2i times 2i. I don't think I need to do that. I think I can square 7 and just write the answer. And I think I can see 7 times 2i out of this. Oh yeah, 7 times 2i. and it happens twice. And when you square 2i, you got to do 2i times 2i, which is 4i squared. And what did we say I squared? The purpose of I squared is to change the sign of the number in front of it. (45 plus 28i), and I'm told they show up on your SATs, achievement test. So, and if you're going into electrical engineering, you'll work with imaginary numbers. Not too many people go into electrical engineering. I had one student that did. Dennis Kennedy was a very well-known and well-liked English teacher here. His son was in my AP Calc class. And when he started, I thought, man, maybe the level's too high for him, but he worked his tail off. And by the end of it, I was pretty darn impressed by the kid. And did I think he'd actually go into engineering? No. And is electrical engineering supposedly one of the toughest engineering classes? That's what I've been told. 250 kids went into electrical engineering. He went to the University of Vermont. Only 10 kids graduated out of 250. Everybody else dropped out. He was the only kid that did it 4 years. So I guess something happens after you leave high school and maybe a maturation. I don't know, but more power to them. All right, 8i to the 19th. Today we talked about writing I to the 19th as I squared. So I to the 19th could have been written as I squared. 10 times is too much, so I'll go 9. Well, that only gets me up to 18. I better throw another one in there. Oh, okay. So I could have written this as 8 times I squared to the 9th times I. Now I could change the sign of the 8, but you know what? The operation that's more challenging is power to power. So this is the same thing as saying, I'll go over here because I don't want to lose the board here. So this is I squared is -1. And this power is affecting the base. It's not affecting the 8. So I got to do -1 times -1 times -1 9 times. And then I got to multiply it times 8 times I. We talked about an odd exponent power here, an odd. Okay, and if it's odd, in other words, we don't look at odd or even at the start. We look at whether it's odd or even after we put I squared in the parentheses. And so that becomes 8 times -1. This stays a negative. Times I, final answer minus 8i. Okay, moving right along. Okay, so you're going to try to write all 3 equations. I don't think A block. I don't think I gave you this. This is a square root function. Okay, it's a square root function. I'm just going to hand that to you. Let me get my eraser here. All right, so can you name all 3 functions? I'm just going to write the answers and you pause and try it on your own. So this one over here, I can start with a 2. I know I'm going up 98. I know that I'm 9 to 14 is 5, and I started with a 9. Okay, I'm sure you probably put 2 over here. That's fine. I just wanted to write it from left to right. This time I won't. This time I'll go with x minus 9 squared plus 2, right? And 9 to 14, when I put 14 in this equation, I get a different answer than when I put 14 into this equation. Very big difference when I use the number 14. I'm dealing with the squared situation. So that becomes 25. And then, where the hell am I? Excuse my French. Oh yeah, changing from 2 to 100, that's the same. Okay. That's a square root function. Acts like a parentheses. I'm starting with a 9. Okay, and I know I wanted 2. Now I want 14 to become 100. I used to, when we used to teach full year classes, I would give this as a challenge question. Usually somebody come in the next day having it right, and then 2 or 3 more people would follow suit. And I would leave it out as a challenge. And I hope that kids continue to look at it, students continue to look at it. So if you want to make it a challenge, don't watch this part of the video. All right, so I plug in what? 14. And if I plug in 14, I don't get either of the two that I had before. I get that. I don't want that because that plus 2 does not take me to here. 98 does. Now I can't use any number smaller than 9. I can't use a number like 8 because 8 minus 9 is the square root of -1. We know that's imaginary. And the Cartesian coordinate system, named after René Descartes, that's the Cartesian coordinate system. René Descartes was a French philosopher, I don't know if it's 1500s or 16. But anyway, it goes way back. Yeah, he was a friend of mine. Those are only real numbers. Okay, square roots of negatives are imaginary. Square root of 0 is fine. So when I plug a 9 in, I get 0. Square root of 0 is 0. 0 times anything is 0 plus 2. Gets me started. When I plug in a 14, 14 minus 9, square root of is the square root of 5. Square root of 5's cancel. 98 plus 2 takes me where I want to go. And I didn't need a GPS. All right, we ended class with this problem, an exponential function. We did Newton's law of cooling with the coffee cup, right? But now it's just mechanics. All right, so y equals 20 is the asymptote, which means that this thing is decaying. And if, we talk about, there's my height. Plus 3. Okay, and these are y values. All right, and this is in feet. I'm about 6 feet, right? Hell no. I used to be 5'9". I'm 5'8¼ I'm shrinking. So bad. But let's say I'm 6 feet, and that would give me an answer of 9. All right, but what if I cut it in half? Oh, it's not 9 anymore. And what if I cut that in half? 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 I guess I'd be going to a height of 3. I'm melting. I'm sorry. Get a little crazy when you get up early and you do math this much. All right, so what's an exponential function? An exponential function is the a b to the x plus c format. The c is your constant, and this is either in the past, I used to be 20 feet high, or in the future, I'm going to be 20 feet high. But one way or the other, you have two kinds of functions. You have growth, right? And this is where your constant is. Things aren't changing much. And why aren't they changing much over here? If I'm cutting something in half, because what the hell am I talking about now? If you take a number like 0.001, it's a number. If you cut it in half, 0.0005, right? That really hasn't changed much visually. You certainly couldn't put it on a Cartesian coordinate system and see the change, right? So it appears constant. So all exponential functions have a constant. I tend to write the exponential functions as y equals c plus ab to the x. My YouTube channel has plenty of practice with exponentials, e to the x, ln of x, so we'll get there. But we got to start somewhere. If you already knew how to do it, I wouldn't be talking to you right now about it. Okay, so how do you write this equation? You start with y equals 20, and then you look at how far your next y value is, 105 from 20, and it appears to be 85. Yep, 85. So that's what comes next. The next jump certainly isn't 85. What would you say? I'd say that's about a third of that. This is about a third of that. So I think I've got exponential decay. And this is going to be close to a third when we find out how far it is from 20 to 44. 24. 3 times 24 is 72. So it's not the best drawing, but maybe it's somewhere between a third and a fourth. That's an accurate statement. All right, that takes care of the y values. That's shown, and that's shown, right? If you do the math here, there's your 20. There's your 105. There's your 44. So now let's use t in exponential functions, because we got a lot of exponential functions, right? You got one right now. You got this exponential function, I think. It's not exponential. Yeah, it's kind of exponential, no, I think that one was higher, that one, then there was this one, and right now we're here. Unfortunately, we're here. Hey, Omicron. Sorry about that, but it's growing exponentially in certain places. So, you got 500 people, and if it doubles in 2 days, you got 1,000. Unfortunate, but that's the nature of the disease. Oh, I haven't finished this yet. So I gotta make a 3 a 0 because I know what anything to the 0 is, and I want you to know what anything to the 0 is. It's 1. And I can multiply 1 by all kinds of things. I can multiply Joan of Arc by the number 1, and I can tell you what I get. So let's put a 3 in. 3 minus 3, 0. Anything to the 0 is 1. Oh, I get 85 plus 20. Oh, that's 105. Oh yeah, 3 gets me 105. Of course, there's change here, right? 3 to 50. That seems like maybe 47 minutes if we were doing one of these Newton law cooling problems. 47 minutes. So I think I want to show that there's an elapsed time of 47 minutes in this problem. I guess I'm going to throw 50 in. Let's do the math. 50 minus 3, 47. 47 divided by 47, 1. Oh, that's my mathematical paintbrush. 24 over 85 to the 1, 24 over 85. 85 times 24 over 85. Oh, that's 24. 20 plus 24. Oh, 44. An exponential function is born. Now, you're not going to do it as fast as me. I've done this at least 100,000 times. All right, that's why I'm just throwing it out there right in front of you. You got the rest of the semester. You want to learn it? Play the video a couple of times. Go to the YouTube channel. Try some other ones. When you come in on Monday, there'll be one on the board. There'll be one on the board. You'll get a chance to do it at your own pace. All right, 2 more problems. 2 more problems, then I'm done. Okay, working knowledge we're after. Working knowledge. Okay, right out of Algebra 1, solving this equation. However, I'd like you to graph it first, a graphical solution, because I don't think you've practiced that ever. Let's get a graphical approximation and see what you get. Okay, so I'm going to do that. All right, I have graph 1 on the left. Y equals x squared plus 5x, and I have 14 equals y. Now I know what that one is. That's a constant. So let's go y equals 14 right there. Let's put it there. Of course, something major happens when I put that there. Then that means I have a new ruler, and that length is 14. I can estimate everything off of that. All right, what's x squared plus 5x look like? Well, I know it's a cup shape up. The question is, can I get some data? Well, we haven't done this too much. We did it a little bit, but I think I'm going to write it this way. I'm going to write it that way. That gives me some initial information very quickly. That tells me the roots. I know when this thing equals 0. -5. If that's 14, I'm going to put -5 right about there. -5 gives me 0. Okay, I've used -5. What number do I put in place of x to get 0? I guess I better put 0 in. And we know it's cup shape up. So that's my vertex, -5 halves. That makes sense. I don't know how far down I'm going to go. So I'll just do something like that. I really don't know that y value now. It's not important to me, so I'm not going to go find it. But it sure looks like I have a small positive number here in terms of magnitude and a bigger negative. So if I get something like 3 and -10, I'm going to be happy. So now let's go back to Algebra 1. Let's look at what you studied. So from a geometric standpoint, I don't know if you know this or not, but that's the area of a rectangle. And we want that area to be 14. That's what I'm looking at. I'm looking at an area of 14 coming from putting some numbers in for x. Well, what's the best way to do it? Well, if you were taught how to do this, then you would have moved the 14 to the other side and you set it to 0. because that makes a new rectangle. And we're now tasked with, can we find the length and the width? Hope so. I hope so. I know that I gotta have an x and an x in order to get x squared. So I'll put a little parentheses there. Oh, 14. Well, I got a feeling that's a 2 and that's a 7. Because I can see the 5 in between. And I want positive 5. So that's positive 7 and negative 2. Oh, I guess I found my roots. Positive 2 and negative 7. Sounds reasonable. Sounds reasonable. Yep. Well, that's how you do the problem. Quadratics are rectangles. If you can put rectangles into the length times width equals area format, and if you know the area is 0, then you either have to have a length or a width of 0. So if I make this height of this rectangle 0, let's make it 0. Let's erase it. What happens to the area when that height becomes 0? Oh, there's no area. That's why we set things to 0, because we're hoping that we can solve by factor. And what does it mean to factor? To rewrite the problem as a multiplication problem. So last statement, I could rewrite this as x plus 7 times x minus 2 equals 0. And I can see numbers jumping off the board at me. Okay, last thing here. Last thing, I don't usually give homework, but in a remote, I certainly do, because we don't get as much done in a remote. There's just no way. But I think we're moving along, pretty good clip, and seeing some thumbs in a lot of places, so that's good. All right, so I'm going to put some numbers in here. I'm just going to show you that we can write equations here as quickly as we write the equation of a line, except I'll be talking through it. Okay, but yeah, a month from now, most of you will be able to just look at that and write with the equation. There's an infinite number of ways of writing this. I can use the sine function, the cosine function, and you could just give me a couple of places and, infinite number of ways of doing it. But I'm going to tackle what I think is the easiest one and the one you see the most often. And it's based on the cosine of 0. Right? Remember what 0 is? It's a place on the circumference of the circle. And I hope you know that it's here. All right? If I want to start walking around the circle, well, then that's pi over 2. That's halfway, right? That's pi. That's 2 pi. When I go all the way around, it's a pretty ugly circle. Reminds me of the attack from Mars. Looks like a saucer or something. All right. So I talked today, at least in one of the classes, about trig being a 2-step solution. The first step being get on the circumference of the circle. And then you do what? You draw your triangle, you find your reference angle, and you look at the ratios. That's what we're doing, okay? This problem, as I was thinking about it today, is actually a 3-step problem, right? And I'm going to do it in the conceptual way that it has to be done when I throw some numbers in there. You will not do it that way mechanically a month from now. A month from now, you're just going to identify some numbers and write it out, just like that. Same way you write the equation of a line. Some of you have maybe got the quadratic down, how you do that, okay, so on and so forth. I got to stop saying okay. Next time I say okay, tell me it's not okay. Okay? Well, that didn't work. All right, so I'm just going to get some random numbers. Let's say that the average temperature yields itself nicely to temperature in New England. Now let's go to an alien planet. Let's go to an alien planet. Average temperature on an alien planet is 500 degrees Celsius, right? But sometimes the highest temperature you get is let's say 547. Okay, and the lowest temperature you get, and we'll do it over here. Lowest temperature you get is 453. Oh, I got to write it to that. 453. Okay, I like that. Yeah, obviously I went up 47 and I went down 47 if my math is correct. At this stage of the day, it might not be. All right, but that's called the amplitude. Well, haven't written the function yet, so I can't talk about it. Okie dokie. Is there a most important temperature on this planet? Not really. You got to go with what you got to go with. But sure seems like if there's a pattern writing it mathematically, it starts here. Because I'm either above it or below it. And there's a logical progression. All right, so I see something that has a pattern to it. And so my challenge as a mathematician is to write what I see. Well, the first thing I see is 500. I definitely see I'm going up 47. And this is a max. And I know I want to use the number 0. So I know I've got to figure out what the cosine of 0 is. Cosine is width. Oh, doesn't have any height, but the width sure looks like it's 1. In fact, sine and cosine functions never get bigger than 1. They never get bigger than 1 unless we do something called amplify. Sound waves. Amplification. All right, that's what happens in this problem. I'm taking the plus and minus, all the numbers between plus and minus 1, and I'm making them 47 times bigger. The biggest thing that comes out of this is plus 47, and the smallest is minus 47. Here's the fun part. Okay. First off, when you do cosine or sine, you have got to be somewhere on the circumference of the circle in order to draw your triangle and look at the ratios. So let me show some random numbers here. Let's say on this particular planet on day 29, it hit that temperature. And then let's say over here at day 100, it hits that temperature. Well, what do I see? I see this. That's what I see. Yeah. And then it starts to do what? Repeat, repeat. Well, what repeats itself? Try walking around a circle. So I want to represent this with respect to where would I be? If I made this number 0, and we know how to do that, right? We can make 29 0 with a simple statement. Then the question is, how far did I go around the circumference of the circle? Once around, right? Then everything repeats. Okay, I mean, what happens when I start going around the circle? The width, I draw that. What just happened to the width? What happens when I draw the triangle up here? What's happening to this width? It's decreasing. That's why I chose the cosine function. I've got something that's at a max and it's decreasing. So I chose that. You wouldn't know to do that. You're just starting to study. You're just starting to think about it. So I know I'm working with x's. I know I'm starting with 29, but I want that 29 to act like starting on the circle. Okay, somebody's calling me now, but I'm not going to stop because I'm almost done. All right, so that's right. Well, this phone's going off, so I'm just going to finish this. All right, so that's that. Now I'm looking at, well, if that's 2 pi, once around the circle is 2 pi, right? Then I guess from here to here is 1 pi. Yeah, the widths on the circle, when I go 180, yeah, the widths aren't positive 1, they're negative 1, and that's a minimum. So that's 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. Sounds like a polka. That's what I need. I need to go from max to min, 0's max, pi's min, max, min, max, min, max, min, whatever. Okay, but I got some numbers that got to make that happen. 29, oh yeah, that's just like a linear function. When I throw 100 in, you know, if I'm not mistaken, when I throw 100 in there, I get 71. I want this kind of activity, all of the widths in the circle. And I want to do it going around the circle 2.5 times. And that's going to match up with this. So let's put 100 in. What's 100 minus 29? 71. What happens to the 71? I've done another conversion, and this class is about conversion. So that gives me the cosine of 5 pi. 5 pi is over here. What's the cosine of 5 pi? Oh, that's -1. What's -1 times 47? -47 plus 500 gives me 453. Yeah, that's it. Ciao. See you tomorrow in class. Play the video as many times as you want. Don't kill yourselves. All right. I guarantee you that over time, you'll pick it up. Just takes a while. Ciao, ciao.